Okay, thank you very much. I'm Taichi Kawamura from Institut de Physique de Globe de Paris, and it's my great pleasure to join this lunar marathon today. And today I will talk about some Japanese challenges to the moon. And as you always, everybody might already know, we are once going back to the moon. And here I think it will be a very nice opportunity to look back what he have done. And especially since I am Japanese, I would like to give a short review on what was the challenge that was done in Japan. So here will be my outline of my talk. I will talk about a little bit of the history, and I will mainly focus on scientific output we obtained by Kaguya mission, which is the first Japanese exploration to the moon. And I will conclude with some future challenges that we are trying to explore. So here you see an overview of historical lunar probes. So it starts from the Luna mission, Apollo mission. We have also Chang'e mission. And you will find Japanese mission right here. So one in the circle is called Kaguya. Basically, it was called Selene, but in Japan, we always give a Japanese name when it succeeded. So we gave a Japanese name, Kaguya, which is a princess of the moon. And I would also like to point out there's two other missions, Hiten and Lunar A, which also was planned or took place in Japan because they are very much important to talk about Japanese history. So I would just start by briefly introducing you Hiten, which was the Japanese very first lunar mission, but it was not scientific mission. It was more on the engineering mission. So the aim was to demonstrate the orbiter manipulation technique or swing by technique. So this was the Japanese first attempt to do such experiment on the moon. So on the other hand, this was not the scientific mission. So we only had dust counter on board as a scientific instrument. And unfortunately, this did not provide any scientific results. In the end, the mission impacted on the moon, and this image right here, you're seeing right here, is the last image that Hiten took before impacting on the moon. The second one I want to introduce is Lunar A, and maybe you remark that this does not have a Japanese name, which means that this was canceled. So this Lunar A was selected as the first scientific lunar mission, the aim was to take this missile type spacecraft, you see here, yes, and impact this on the moon. And inside this probe, we have seismometer, we have heat flow probe, and the idea is that we drop it from the orbiter, let it penetrate into the ground and do the observation. And I think you can easily imagine that this is very, very difficult. So the development took many time and it was postponed, there was delayed, and in the end, in 2007, this was chosen to be canceled. So these were the two Japanese missions that took place or that was going to take place, but finally canceled. So this was what was happening in Japan. So what was the global trend of the lunar exploration back then? So I think everybody knows that from 1960s to 1970s, we had an era where US and Russia tried to land on the moon. So this was a time where we aimed the landing on the moon. So if we take the Apollo, for example, it's landed on the moon. They collected many samples. And what was very important was they deployed some instrument on the lunar surface, including magnetometer, seismometer, heat flow probe. And these are still the very important data that we have right now because since then we have not landed on the moon. If we step a little bit forward in the history and go to 1990s, we come back to some different era where we use orbiter to explore the moon. So there's a Clementine mission and Lunar Prospector mission. So the big difference between Apollo and these two missions is that Apollo focused on the science around the landing site. On the other hand, these Clementine and Lunar Prospector focus more on global observation. Here, I'm showing you one example where there you see the thorium abundance on the moon. And here, it's a small dot, but you see the Apollo landing site. What happened is that while Apollo provided very important pieces of information, we finally found out that they were not the representative site on the moon, as you've seen from this figure, because this falls in this region, which is called PKT, which is very rich in radioactive elements. So I will say first lunar mission was more on local detailed analysis, including sample returns. And the next step was the global observation, including first light. With this trend, we Japanese programmed this Kaguya mission. So this was the first exploration to the moon, Japanese exploration to the moon succeeded. And this was launched on 2007 and impacted on the moon 2009. And this consists of three spacecraft, one main orbiter, as you see here, and two relay satellites. Given the context of the trend of the space exploration, the lunar exploration, there was two main objectives of Kaguya. First is to perform the global observation. So we learned that Apollo landing site is not necessarily the representative site of the moon. So we thought that it's very important that we have a whole coverage of the moon to have the global view of the characteristic of the moon. And another important thing is to perform a multi-instrument observation. It is very important that we observe like a crater or some characteristic topography with different eyes. So which means using different scientific instrument. So what we wanted to do is to have a global view and a multi-point of view. With this aim, Kaguya was equipped with 14 scientific instruments and the 15th instrument, which is more for the outreach objective. I will not go into the detail of each instrument, but I would just want to briefly point out that this series of instruments focused on different aspects of lunar science. For example, the top one, X-ray spectrometer and gamma ray spectrometer, focused more on elemental distribution. And there's a part we focus on mineral distribution, surface structure, subsurface structure, and we also observe the environment around the moon. And finally, we also measure the gravity field. So you see how rich this mission was equipped, and this will give us very much multiple point of view to understand one phenomena that we see on the moon. And this is exactly the strength of Kaguya mission. With that said, I would like to discuss a little bit more on science highlights of Kaguya mission. I listed 4, and finally, I would like to conclude by, well, these 4 observations tell us about the moon. Let's talk about observation of the far side gravity field. When we say observation of the gravity field, it might not be very straightforward to you, but how we do it is we just track the orbit of the satellite very precisely, because when there's a gravity difference or gravity anomaly, we know that the orbit will be shifted. So it changes the orbit following the gravity field. So it is very important that we track the satellite very precisely. And this caused a problem on the moon because the moon is always showing the same side to the Earth. In other words, when the satellite is on the far side, it is always invisible. And this is a huge problem when we want to track the orbit of the satellite. So you see the figure here. So this is the antenna on the Earth. And if you see the satellite, it's okay here, but it's once the satellite goes behind the moon, we cannot track it. And the orbit, the precision of the orbit will be very low. This resulted in the lower resolution of the gravity field on the first side. So this is a gravity field obtained from lunar prospector. And here you see the near side and the far side. And I don't know if you can see this vertical line that we see on the gravity field of the moon, which is not visible on the near side. This is exactly the artifact we have because we kind of guess the orbit because it's not visible. We do much better than guessing, but still we have these kind of artifact that contaminates the true gravity field. And the aim of Kaguya is overcome this problem by using the relay satellite. So the idea is that we have this antenna on the Earth, and we have the relay satellite, and we let the relay satellite communicate with the main orbiter. So we call it the four-way communication because this one way and two. So basically, it's always one way and two way. But in this case, we have 1, 2, 3, 4. So we use this four-way communication method to resolve better the first side gravity field. So you see the result over here. And you see that this we have much better resolution, and we don't see any more this vertical line, which was the artifact of the that comes from the fact we don't see the orbiter. So what is so interesting about far side gravity field? So here I'm showing you some result from Kaguya. So there's a topography, and there's a two types of gravity field that is observed from by Kaguya and crustal thickness. And this shows already a strength of Kaguya mission because topography is also obtained by Kaguya. So I would like to draw your attention to the crater here. So here you have the 3 craters here on the near side, and the other 3 craters, or I should say basin because they are large ones, you see it on the far side. So I think you now see this circle shape as a crater, and let's take a look on the gravity field. So if you see the gravity field, you see that this also stands out from the background. And if you see the near side basin, it's red. On the other side, and if you see the far side craters, it's blue. So if I were to give you how to read this figure, when it's red, it means that we have a positive anomaly. In other words, we have something heavy on the subsurface. And when it's blue, we have something light below. So this already shows that we have a significant difference between the crater or basin on the near side and far side with respect to their subsurface structure. And what does it tell us? So we see something heavy for the near side craters, which means that we see mantle material, which is heavier than crust, getting up. So we see some mantle material that is that was lit up, creating this positive anomaly. On the other hand, this did not happen for the far side. And the question is, why do we have such difference? And the one key point is that the temperature of the near side and far side was very much different, as well as the crustal thickness. What happens is that the near side crust is thinner and hotter, so it was much more easier for the mantle materials to come up. Thus, we see this positive anomaly. On the other hand, the far side crust was thicker and colder, which is more rigid. So this compensation or lifting of the mantle material did not take place. So this shows very clearly that we see 2 different types of crust for the near side and far side of the moon. So let's go to the next discovery of the Kaguya, which is what we call PAN. PAN stands for purest anosocite. Anosocite is a typical mineral we see for the lunar crust, and Kaguya made a global survey of this mineralogy of the crust, and we found this PAN. So it is normal that we find anosocite in the crust because this is a main composition of the crust. But what was surprising was this anorthosite was pretty much pure, pure plagioclase. So the main mineral of the anorthosite is plagioclase, and usual crust materials contains about 80% of plagioclase or 90%. But what was surprising is that we also found plagioclase in the anorthosite, which is almost 100% plagioclase. And if you take the process of crystallization from magma, it is very surprising that we have such a pure anorthosite on the lunar crust. And the strength of the Kaguya is we did it on the global scale. So we were able to map this on the lunar surface. So this, every point, white point you see is where we found pan. And we also have the pink ones, which is eroded pan. So which is pan, but in a sense, we see some degradation of the characteristic. So we did what scientists did is we did a data mining of spectral data, which is already amazing. We have 70 million spectra, and we mapped everything here. So what we can say is we found pan, and this is almost ubiquitous on the moon. We find it everywhere on the moon. And the question is, how can we get such pan globally on the moon? And the one idea to solve this is to have the global magma ocean. So this idea of magma ocean came from Apollo era. So it means that the lunar surface was completely molten. And when they crystallize, they start from olivine, which is heavy, and zinc, which create the mantle. And then we start to crystallize plagioclase. And this is light, so it will float in magma. And the shallow part of the magma will be filled with plagioclase. And through this process, we are able to create the crust with almost purely made of plagioclase. So what this pan, existence of pan, and the global distribution of pan tell us is that the lunar crust formed from the global magma ocean with the process that enables us to select the plagioclase into the crust. I would also like to talk a little bit over about, so I talked about crust, so I would like to talk about the mantle. So another discovery of the Kaguya mission was they finally found olivine. So olivine is a good marker of the mantle material. And again, we did the global survey and we mapped everything on the map. Maybe it's not so visible here, but every red point here is a point where we found olivine, or where we found mantle material. And I think you can see that this red point almost concentrates around big basins, which means that this mantle material, olivine, was excavated by large impact. And what is interesting is that this, meaning that this was excavated by impact, is that yes, this is coming from mantle, but this was relatively shallow region of the mantle. Finally, I would like to say a few words on magnesium number. So I think people will pose the question, what the heck is magnesium number? In short, magnesium number is when we compare magnesium and iron, which do we have? And what this is interesting is that we know that when we crystallize magma, we first get magnesium, and then we get the iron. So if we have more magnesium, this means that this crystallized at the early stage of the crystallization. Vice versa, when we have more iron, it means that this crystallized at the late stage of the crystallization. And what was interesting is that Kaguya did this survey, again, globally, and we found that far side and near side had significantly different magnesium number. In short, far side crust was rich in magnesium and near side crust was rich in iron, which means that far side crust is older compared to the near side. So I rapidly showed you 4 discoveries made by Kuya: observation of the far side gravity field, PAM, olivine, magnesium number. What does it tell us on the history of the moon? So I will not repeat everything, but in short, what we found is the crust is very different from the near side and far side. At the same time, this was made from the crystallization of magma. So now what we found is that possibly moon was covered with global magma ocean, and it started to crystallize from the far side. So far side crystallized first, and then this growth expanded to the near side. So that is why we have older crust on the far side and newer crust on the near side. And this also falls very well with the existence of PKT, which is the rare earth element concentrating on the near side. So by doing global survey and multi instrument observation, because we have gravity observation, mineral observation, element observation, and putting this together, we were able to uncover such a history of crystal formation of the moon. I would like to conclude shortly by introducing some Japanese future challenges. We have SLIM, which is the Japanese first lunar landing mission. This will previewed on 2022. You have the example here. So this is a Japanese mission that land on the moon. So it's Japanese, so we bow when we land. So you see this very characteristic landing system. We also have LUPEX. This will be the first Japanese landing mission to the pole. And we will search for lunar ice. Finally, Japan will also participate to international space exploration, which is also take part as a part of Artemis. And JAXA is now preparing to proposing to do some 3 topics on the moon to sample return, to build a lunar telescope, and make a global seismic network. So it was pretty rapid, but I wanted to share this some Japanese lunar challenges, what we have done, what we are going to do, with some scientific implication of Kaguya mission, which is at this point which was the most successful Japanese lunar exploration mission. With that said, I will conclude. Thank you very much, and I will be happy to take any questions.